Have you ever pondered over the relentless march of time and its effects on our aging process? Here on Earth we live our lives on the assumption that time is a constant. It moves forward, never backward, marking the rhythm of our existence. Each tick of the clock nudges us forward into the future, and with it we age. From the moment we're born, aging is the one universal truth we share. It's a byproduct of the passage of time, a process that affects every living creature on this planet. But what if I told you that these fundamental concepts of time and aging, while seemingly straightforward, become much more complex when we venture beyond our terrestrial boundaries? When we reach for the stars and explore the vast cosmos, we encounter a reality that seems to defy our terrestrial intuition. We find ourselves in a realm where the rules of time as we know them start to bend and twist. Here, in the vacuum of space, the constancy of time, the inevitability of aging, all seem to waver. This is a realm where the speed of light, a blistering 300,000 kilometers per second, sets the pace for everything. Where the immense gravitational pull of celestial bodies can warp the very fabric of space and time. And it's here, in this mind-boggling expanse of the cosmos, that we encounter a phenomenon that challenges our conventional understanding of time and aging. A concept so strange, so counterintuitive, that it seems to have been plucked straight out of a science fiction novel. But this is no fiction. This is a real, scientifically verified phenomenon that has profound implications for our understanding of the universe and our place within it. As we delve deeper into the cosmos, we encounter a phenomenon that challenges our conventional understanding of time and aging. Time dilation. Time dilation, a concept birthed from Einstein's theory of relativity, introduces a new dimension to our perception of time. Now, this might sound like something straight out of a science fiction novel, but it's a very real phenomenon that has been proven through numerous experiments. So, what is time dilation? In simple terms, it's the difference in the elapsed time measured by two observers due to a relative velocity between them or to a difference in gravitational potential. In other words, time can appear to move slower for an observer who is moving at high speeds or is in a strong gravitational field compared to an observer who is stationary or in a weaker gravitational field. Now let's take a closer look at how this works. At the heart of time, dilation is the speed of light, which is a constant 300,000 kilometers per second. According to Einstein's theory of relativity, the speed of light is the same for all observers, regardless of their motion or of the motion of the source of the light. So imagine an astronaut traveling in a spaceship at a speed close to the speed of light. According to the time dilation formula, T equals T divided by the square root of 1 minus v squared over c squared, where T is the elapsed time for the astronaut, T is the elapsed time for someone stationary on Earth, v is the velocity of the spaceship, and c is the speed of light. As the spaceship's speed v approaches the speed of light c, the denominator of the formula approaches zero, which makes t, the astronaut's time, longer than t, the Earth observer's time. This means that time moves slower for the astronaut compared to someone on Earth. Similarly, gravity can also cause time dilation. The stronger the gravitational field, the slower time passes. This is why time on the International Space Station, which is in a weaker gravitational field than Earth, moves slightly slower than time on Earth. Thus, time dilation suggests that time can indeed slow down for an observer moving at high speeds or in a strong gravitational field. Now you might be wondering, how does this time dilation affect aging? The answer lies in the fabric of the universe itself, the space-time continuum. Let's take a trip to space. Here we encounter two types of time dilation: relative velocity time dilation and gravitational time dilation. The former happens when an object moves faster, while the latter occurs near massive objects. In both instances, time slows down. Consider an astronaut aboard the International Space Station. As they orbit the Earth at breathtaking speeds, they're experiencing relative velocity time dilation. In other words, time for them is passing slower than for someone stationary on Earth. At the same time, they're also experiencing gravitational time dilation due to the mass of the Earth. This means that time for them is passing even slower. These two effects combined mean that our astronaut is aging slightly slower than their counterparts on Earth. Now, you might be thinking, do astronauts return to Earth as youthful as the day they left? Not quite. The effects of time dilation on human aging are incredibly small. After 6 months on the International Space Station, an astronaut would age approximately 0.005 seconds less than someone on Earth. Still, this minute difference is a testament to the remarkable reality of time dilation. It's not just a concept confined to the realms of sci-fi and theoretical physics. It's happening right now as astronauts orbit our planet. Imagine returning from a space journey to find your twin sibling slightly older than you, a reality made possible by time dilation. So let's revisit what we've uncovered about time, aging, and the enigmatic phenomenon of time dilation. We've discovered that time dilation is a physical phenomenon explained by Albert Einstein's theory of relativity, which tells us that time can move differently for observers in motion relative to each other. This means that the faster an object moves through space, the slower it moves through time in relation to another object. We've learned that there are two types of time dilation. Relative velocity time dilation, which is caused by differences in speed, and gravitational time dilation, which is due to differences in gravitational fields. Both can occur simultaneously, and both have fascinating implications for the universe and our understanding of it. For example, astronauts on the International Space Station experience both types of time dilation, causing them to age slightly slower than people on Earth. And if an astronaut were to travel at relativistic speeds, they would experience time passing more slowly compared to people on Earth. The exact magnitude of the time difference depends on the speed and acceleration of the spacecraft. As we continue to explore the cosmos, the mysteries of time and aging will continue to challenge and fascinate us. Who knows what we'll discover next? Before we wrap up, let's take a look at what might be on the horizon for our understanding of time and aging. In the world of science fiction, the idea of time travel has always been a tantalizing prospect. But could it actually become a reality in the light of our understanding of time dilation? Well, while it's currently beyond our technological capabilities, some physicists believe that it might be theoretically possible. For instance, if we could build a spaceship capable of near light-speed travel, we could theoretically slow down time for the passengers aboard, effectively sending them into the future relative to people on Earth. Similarly, if we could create a gravitational field strong enough, we might be able to slow down time and thus age more slowly than the rest of the universe. However, these ideas are purely speculative and come with their own set of challenges and paradoxes. But who knows what the future holds? Perhaps one day we'll unlock the secrets of time travel and control over aging. But until then, we continue to explore, to question and to marvel at the mysteries of our universe. Until next time, stay curious.